Hey everyone, welcome back. Today we're going to be continuing our journey of learning to develop games for the Sinclair Spectrum computers by looking at how we can do loops. Now in BASIC you're probably familiar with the for next loop, which allows us to do looping in our programs. But in Z80 assembly language, of course there are no for next loops, so we need to find some other methods of accomplishing the same task. And we're going to look at a couple of those methods today. So if you're ready to go, let's get started. Alright, so as usual I have my ZX Spin assembler and emulator installed on my computer, and if you need instructions on how to install it and use it, I have a video you can watch that will explain that. And there's actually two methods that we're going to look at today for using loops in our Z80 assembly language programs. One method uses 8-bit numbers and the other uses 16-bit numbers. So let's go ahead and take a look at the first program, which I have on my screen here, and we'll just go through it line by line. So the first line, of course, is our org instruction. So this program is going to be saved in memory at location 30,000. And then I've laid out my programs in a structured format. So I'm going to actually start at the bottom so we can familiarize ourselves with the different parts of my program before we actually get into the main program loop. So let's start by going down to the bottom here, where I have a data comment, which is indicating that I'm storing some data in my program. And by data, I just mean bytes of data that I'm storing in the memory. So as you can see here, there's only one line in this data section, and it has a label called counter, and it's followed by a define word instruction, which we should know by now saves 2 bytes of data in memory. And the value that I'm saving here is the value of 0. So this instruction, as we know, will store a value of 0 in 2 memory locations because I'm using the define word instruction. And that memory location, or those 2 memory locations, will be pointed to by this label here that I've called counter. Now let's just go up to our previous section here, which is labeled ROM Routines. And my ROM Routines section is where I assign numeric values to labels that represent the location of ROM routines in the Sinclair Spectrum computer. So for example, you can see here, I've assigned 2 ROM routines. This one with the label called ROM1. I've given a value of 5633, which is the address location in ROM where this particular ROM routine lives in a Sinclair Spectrum computer. And the purpose of this ROM routine, as we can see here by the comment, is to activate the output channel per A register. And the way this ROM routine works, as you probably know from watching my previous video, is that it's going to activate whatever output channel we have specified in the A register. And in this program, for example, we're going to be using a value of 2 because 2 represents the upper portion of the screen on a Sinclair Spectrum computer. So we want to print to that large upper portion of the screen, which is output channel 2. And in order to activate that channel, we need to call this ROM subroutine. And if we take a look at the next ROM routine I have configured here, it has a label of ROM2, and I've given it a value of 6683. And this is another ROM subroutine that lives in the Sinclair Spectrum computer's ROM memory. And what it does is it prints the value that's in the BC register pair to the screen. And you can see here there's a note that says 9999 max. That means this printing subroutine can only handle numbers up to a maximum value of 9999. And we also covered that in a previous video as well. Alright, now let's back up one more section here, which I've labeled subroutines. And the subroutine section is obviously where I keep all the subroutines for my program. And you can see in this program, there's only one subroutine called sub1. And here is the return instruction for that subroutine. And we'll be taking a look at the subroutine in a moment. So now let's go back to the main loop of our program right at the beginning. So up here, I have the main program loop starting with a label called main and a comment that identifies it as the main program loop. And let's see how this program is actually going to allow us to use a loop in our Z80 assembly language program. So the first line of the program here, it loads the HL register pair with an address which is pointed to by the counter label. And our counter label is down here, which we took a look at earlier, and it's pointing to this memory location where we stored a value of 0. And this is an address that I'm actually using to store a number that's going to help us verify how many times the loop executed in our Z80 assembly language program. And we'll see more about that in a moment. So let's just remember that for now, that our counter label is pointing to a memory address where I'm storing a number that is going to count for us how many times our loop executes. And we'll get back to that in a moment. So let's go to our next line now, here, which loads the BC register pair with a value of 0. So the BC register pair is going to be initialized to 0 because we're going to be using the B register as our counter. And the way we're going to do that is by using this instruction here, decrement jump not 0, which you may be familiar with already, but we'll get to that in a moment as well. And as you may already know, that instruction uses the B register as its loop counter. So up here, I'm simply initializing both the B and the C register to 0 because it's easy for me to do. So I don't actually need the C register in this case, but I'm just going to set them both to 0 in one shot here by assigning the BC register a value of 0. So now the B register and the C register both contain a value of 0. So now in line 5 here, I'm loading the B register with a value of 10. So 10 is going to be my loop counter. So just like in a basic program, you might have a for next loop, which might say for f equals 1 to 10. So you'll have a loop that executes 10 times. In this case, we're doing exactly the same thing, but we're using B, the B register, as our loop counter. So I'm initializing that with a value of 10. And the next line at line 6 here is where I actually start my loop. And I have a label here called loop to indicate the start of my loop. And that's what my comment indicates here as well. So let's see what's inside my loop. So the first line in my loop increments the contents of the HL register pair address. So you can see here that we've loaded the HL register pair with a value that's pointed to by this counter label. So what we're doing here is this first line of this loop is going to increment the contents of this HL register pair memory address. So down here is the counter label that we used. So we know that our HL register pair is pointing to this memory address that is pointed to by our counter label. So this memory location is where I'm going to be storing, remember, the validator to prove how many times our loop actually executed. So as soon as the loop begins, it's going to increment that value to 1. So this is the first time we're going through this loop. Now let's take a look at the next line of my loop, which is where we have this DJNZ instruction, which stands for decrement jump not 0. So decrement jump not 0, what it does, as you may already know, the first thing it does is it decrements the B register, and then it jumps if the B register is not 0. So it checks the B register after it decrements it and checks to see whether it's 0 or not. So if it's not 0, it's going to jump somewhere. And where is it going to jump? Well, here it's going to jump to wherever this location that's pointed to by the label loop here is indicating. And our loop indicator is right up here at the start of our loop. So when it goes through this loop, it's going to decrement the B register, and it's going to keep jumping back to the start of the loop up here until the B register contains a value of 0. So if we get down to this line here and the B register does contain a value of 0, that means it's gone through this loop 10 times because we initialized the B register with a value of 10 up here. So if it gets down to this line in our loop and it decrements the B register and it now contains a value of 0, that means it's gone through our loop 10 times, it's executed the loop 10 times, and now B contains a value of 0. And so it doesn't jump anymore, it just continues on with the rest of the program. So it continues on to line 9 down here, which is a call instruction, and it's going to call sub1. And sub1 is my one and only subroutine in this program, and let's take a look at what that does. So after our 10 loops have finished executing, this subroutine labeled sub1 is going to get called. And if we take a look at the comment here, it says print loop count verifier. So now our B register has decremented from 10 down to 0, but I want to print on the screen how many times our loop actually executed. And the way we're doing that, remember, is by incrementing the value of the HL register pair address, which is the address down here that's pointed at by our counter label. So what we want this subroutine here to do is we want to extract the value from that memory location and print it on the screen. So that value should now equal the number of times that our loop executed because we incremented that value every time we went through the loop with this line right here, increment brackets HL. So now let's see exactly how our subroutine works. So now after our loops finish executing, we call this sub1 subroutine, which has a comment here, print loop count verifier. And our loop count verifier is the number in this address down here that's pointed to by the counter label. And so the first line of this subroutine loads the value of 2 into the A register. And as we can see by our comment here, it says set output channel value to select top of screen. So this is what we need to do in order to print to the top portion of the screen, which we mentioned in a previous video. And then our next line of this subroutine calls a ROM subroutine, which I've labeled ROM1. And we can see down here, ROM1 activates the output channel per channel A. So whatever value we have in channel A, which in this case is value number 2, it's going to activate that output channel for us to print to. And so in this particular case, it's going to activate channel 2, which is the upper portion of the screen. So that's what these two lines here do. Now we're ready to print to the upper portion of the screen. Let's see what we're going to print there. So the next line here loads a value into the BC register pair. And what value is it going to load? Well, this is the value that it's going to extract from our location down here. So in this line, we're going to load the BC register pair with our loop counter verifier. So every time the program executed a loop, it incremented that loop counter verifier, and we stored that in this memory location down here pointed to by the counter label. And so now all this line does is extract that value and load it into the BC register pair. And the reason we need to load it into the BC register pair is because we're going to be calling a ROM subroutine that prints the value that's inside the BC register pair to the screen, which is what we do in our next line right here. So here we're calling another ROM subroutine, which I've labeled ROM2. And if we take a look at down here, which we looked at before, ROM2 executes a ROM subroutine which prints whatever value is in the BC register pair to the screen. So that's what this line here is going to do. It's going to call the ROM subroutine to print the value of the BC register pair, which is our loop counter, to the screen. And then finally we have our return instruction right here, which in this case, you can see the note says return from sub1. So this is a subroutine, so obviously our return instruction from a subroutine returns back to wherever it called it. And in this case, it's going to return back up here to the main program loop because it was called from the main program loop. And the main program loop up here, of course, has its own return instruction, which returns execution of the computer back to BASIC, because this machine code program was called from BASIC, or will be in a moment when I execute it. So hopefully that all made sense to you. And now let's bring over our emulator and we'll actually try it out. So we can see that the program in this case is stored at memory location 30,000. And I'll just increase the size of this window so we can see it a bit better. And now we want to execute the program that is stored at memory location 30,000. So I've already assembled the program and it's in memory at location 30,000. So I'll execute it now by typing randomize user 30,000. And now, since we initialized our loop counter back here to a value of 10 right here, we would expect that when we execute this program, our loop should execute 10 times and we should expect a value of 10 to be printed on the screen. So let's go ahead and press enter now and see if we get a value of 10. And we do. So we can use this method when we want to loop in our Z80 assembly language programs with a loop counter that's 255 or less. So if we want our loop to execute no more than 255 times, then we can use this method because this is an 8-bit loop, because we can obviously only store an 8-bit number in the B register here. So that means our loop can only execute a maximum of 255 times, because that's the maximum value that we can store in a single byte register. Alright, so now let's see how we can use the Z80 assembly language program to loop more than 255 times. So if we take a look at our program here, my first instruction is of course the org statement, and in this case our program is going to be stored at memory location 33,000. And then we have our main program loop up here indicated by the main label and our comment indicating that it's a main program loop. And then if we take a look down here at the bottom, you can see we're not using a memory location this time to store the counter verifier number, because a memory location can obviously only store a value up to a maximum of 255, and since this program is designed to loop more than 255 times, I can't use a single memory location to store that value for me. So the way I'm going to store that value is up here. I'm loading that value into the BC register pair, and I'm initializing it as 0. So in this case, I'm going to be using the BC register pair to count for me how many times our program executes the loop. So down here in the next line of our program, I'm initializing the main loop counter for the program as 300, and I'm storing that value into the HL register pair. So the HL register pair in this case is what I'm using as a counter for the loops, and our loops start right here with our label called loop and our comment that indicates start of loop. And then let's take a look at what we're doing in our loop this time. So the first line inside of our loop increments the BC register pair, which we now know I'm using to store the value for our loop counter verifier, so I can see how many times this loop actually executed. So we need to increment that every time we go through the loop. And then the next line of our program here will decrement the HL register pair. The HL register pair is our main loop counter, so that's going to decrement, in this case, from 300 down to 0. And it's going to do that by decrementing it right here. But now, unfortunately, there is no instruction in Z80 assembly language to check when the HL register pair gets down to a value of 0, because decrementing the HL register pair doesn't affect the 0 flag in the flag register, so we're not able to use that method to see when the HL register pair reaches 0. So in this case, we need to do it manually. And the way we're going to do that is by looking at these individual registers on their own. So the H register and the L register, we're going to compare them to see if either one of them contains a value that's not 0. And if that's true, then obviously the HL register pair contains a value that's not 0. And the way we do that is right here. And this might seem a bit confusing initially, but it's pretty important to understand this because it's a powerful tool. So just stick with me and we'll get through it and we'll understand exactly how this part of the program works. So what we're doing here is we want to be able to compare the H register with the L register, which we'll do in a moment. But unfortunately, there is no instruction in Z80 assembly language that allows us to compare the H register to the L register. So what we need to do is kind of cheat, and we're going to extract the value from one of the registers, in this case the H register, and we're going to load it into the A register because we can do a comparison on the A register. So now the A register is being loaded with the value that's in the H register, and we can use that to compare to the L register, which we do right here. So this instruction here is an OR instruction, which does a logical comparison of the bits between the L register in this case and the A register, because that's how the OR instruction works. It compares something with the A register. And in this case, we're giving it the L register to do its comparison. So this line is going to compare the bits in the L register with the bits in the A register, which, as we now know, contain the value that was previously in the H register. Well, it still is in the H register, but we've now copied it into the A register as well. And as you probably know, the way an OR instruction works is that if either one of the bits is a 1, then the result will be 1. So the only way that the result of this OR comparison will be 0 is if all the bits in both the H and the L register, or in this case the A and the L register, are 0, then the result will be 0. So what this part of the program does is it effectively compares the value in the H register to the value in the L register to see if either one of them is not 0. So the only way that result will be 0 is if the HL register pair contains a value of 0, which is exactly what we need to check for. And then down in the next line here, if the result is not 0, it loops back up to the beginning of the program right here using this jump relative not 0 instruction right here. So jump relative, as you probably know, it's a relative jump, which is different from a regular jump, which it changes the instruction location of the program to a different address, but a relative jump has limitations of how far it can jump. So it can only jump backwards 128 addresses or forwards 127 addresses. But in this case, since I'm only jumping back to this location pointed to by this loop label, which is right up here, that's not very far back, so it can easily be handled by a relative jump, which is why I'm using a relative jump here. And then the next part of this instruction says not 0, so it's going to jump relative back up to the beginning of our loop only if the result is not 0. So if the HL register pair contains a value that's not 0, that means our program hasn't finished looping, so our countdown hasn't gone from 300 all the way down to 0 because it still contains a value that's not 0. So it's going to keep cycling through this loop until the HL register pair contains a value of 0. And then it's not going to jump. Instead, it's going to continue on with the rest of the program, which is right here, call sub1. And sub1 is right down here. It's our subroutine. And we can tell by our comment here that it prints the loop count verifier. So remember, we're using the BC register pair in this case to keep track of our loop count verifier to see how many times our program actually loops. So let's see what this subroutine actually does. So the next line in our subroutine here loads a value of 2 into the A register, which is going to be used to set the output channel so we can print to the upper part of the screen. And remember, in order to do that, we load a value into the A register, and then we call a ROM subroutine, which activates that output channel. But you can see I've got an extra instruction here before we actually call the subroutine, because once we call this subroutine, it's possible that subroutine could change the value in the BC register pair. So before I call it, I want to preserve the value that's in the BC register pair, and I do that right here by pushing it onto the stack. So I push BC, which will take the value that's in the BC register pair and save it onto the stack, which is a special location in memory that is used for storing values using this push instruction. And then I can call my ROM routine to activate the output channel. And then once it returns from that ROM routine, I go down here to the next line in our program, which will pop the value off of the stack and place it back into the BC register pair. Because now I need to print the value that's in the BC register pair to the screen, because that's the value of our loop counter. And I do that in the next line right here, where I call the subroutine I've indicated as ROM2, which is right down here, which is the same ROM routine we used in our previous program to print the number that's in the BC register to the screen. Now the note here indicates that this ROM subroutine can only be used to print a number up to a maximum value of 9999. So that's okay in this particular example, because remember, I initialized our loop counter at 300, so that's well below 9999. So I should be able to use this subroutine to print this value for me. But maybe, if you like, as a challenge to yourself, if you want to try and figure out how we can modify this program to actually print a value that's higher than 9999, let's say we want our program to loop 65,000 times. So in that case, there is a way we can do that, and we did cover that method in our previous video. So if you want to have a little challenge for yourself, you might want to go back and take a look at that video and try to modify this program to allow it to print a value that's larger than 9999. But in this case, this value is large enough for us because we're only looping 300 times. So now let's go ahead and assemble our program and we'll test it out. So I'll bring the emulator back over here, and this program is being stored at address 33,000. So in order to execute it, I need to type in randomize user 33,000, just like that. And since we set our loop counter to a value of 300 initially, we would hopefully see a value of 300 printing on the screen. So let's try it out and see what happens. And there we go, 300. And now, since we just discussed that this program should be able to handle a value up to 9999, why don't we just go ahead and change this initial loop counter here to 9999, and we'll test that out, and hopefully it works. So there, I've changed it to 9999, and I'll go ahead and assemble it again. And now we'll run it again, randomize user 33,000, and there. So it does work with values up to 9999. And like I said, if you want to, you can try to modify this program to make it work with larger values as well. So there we go. We've learned two very useful techniques for looping in our Z80 assembly language programs that I'm sure is going to come in very handy in our game development journey. And like I said, you may want to go ahead and try to modify this program. And it's not that difficult. We just need to go back and review the information that we learned in our previous video, and I'm sure you'll be able to get it working. So thanks again for watching, and we'll see you next time.